Build a search that finds words and meaning in Python. By the end, you will have a working keyword pipeline, a simple semantic expansion, and a blended scorer you can tune. You will see how exact token matches differ from meaning-based matches, and you will have a concrete baseline to measure improvements against. I'm Professor Pi, teaching search and IR from basics to advanced in simple Python. Keyword search is fast and cheap. It optimizes exact recall for the words a user types. Semantic search improves recall for meaning and paraphrase. The trade-off is memory and ambiguity. Keyword indexes are tiny and fast to update. Semantic expansions use more terms or vectors and cost space and lookup time. At moderate corpus sizes, you can see precision changes from single digits to noticeable jumps when you add simple synonym rules. Think of keyword search as literal string matching. Think of semantic search as widening that match to meaning. Keyword shines when queries are specific. Semantic helps when users paraphrase or use related words. One limit is ambiguity. Adding meaning can bring relevant documents, but also noisy ones. We will build a small pipeline that starts with substring matching, moves to exact tokens, adds light stemming, injects synonyms, and then blends both scores into a tunable final rank. Now we will filter documents by simple substring checks. This snippet filters documents by checking if any query word occurs as a substring. It creates 5 short documents in a list called docs and defines the query queue. A list comprehension named hits scans each document after lowercasing and tests whether any word from the query appears as a substring. Substring matching is the most minimal keyword search. It is case insensitive here, but not aware of token boundaries. The snippet then prints only the first 2 matches to keep the visual result compact while still showing real data. The printed items are the earliest documents that contain either smart or machine, confirming the approach and its strict literal behavior. This quick filter is extremely cheap. It is good for very small corpora and instant feedback. Expect false positives when a query word appears inside another word. Lowercasing helps with simple case mismatches. If you need strict token boundaries, you would switch to tokenization instead of substring checks. Next, we will rank by exact token overlap. This snippet ranks documents by how many exact query tokens they contain. The variable tokens holds the query words split on whitespace and treats them as whole tokens. For each document, the code splits the text into tokens, counts how many overlap with the query tokens, and pairs that count with the document text in a list called scores. The scores list is sorted by descending count, and then by the text itself to make ties deterministic. The snippet selects and prints the top 2 results. This emphasizes exact token matching rather than loose substrings, and shows which documents contain the most literal query terms like smart and machine. Moving to token overlap gives you more precise matches and fewer accidental hits. It also makes ranking intuitive because documents with more shared tokens score higher. Tokenization decisions matter here. Splitting on whitespace is simple and fast, but misses contractions and punctuation handling. Next, we will normalize simple plurals with a tiny stemmer. This snippet improves recall using a tiny stemmer to reconcile plurals and singulars. A lambda called stem removes a trailing s to normalize simple inflections, and qt stores the stemmed query words. For each document, the code stems every token and counts matches against qt, which now lets machines align with machine. It produces scores and sorts just like before, but the normalization treats morphological variance as the same term. The result demonstrates that plural-sensitive documents rank higher because machines now matches machine. This small step bridges common surface form differences without a heavy library. Light stemming is a low-cost win. It increases recall for regular inflection patterns and rarely harms precision in small corpora. If you over-apply stemming, you risk merging unrelated roots, so keep rules conservative for a baseline. Next, we will expand the query with simple synonyms. This snippet expands the query with synonyms to capture meaning beyond exact words. A dictionary named SYN maps smart to intelligent and machine to machines, and EQT merges these with the stemmed query QT. The code scores each document by checking whether tokens or their stems exist in EQT, which now includes semantic alternatives. This turns a purely keyword search into a simple semantic one that can match intelligent even when smart is absent. The output shows the document best supported by both machine and intelligent, illustrating improved semantic recall from a small synonym list. Synonym expansion shifts recall toward meaning. It is lightweight and interpretable. The downside is that each added synonym increases index size and can introduce noise if synonyms are polysemous. Keep your synonym list focused to avoid diluting precision. Finally, we will blend exact and semantic signals with a weight. This snippet combines keyword and semantic matches with a tunable weight. For each document, it computes a set DT of stemmed tokens, then scores the document by summing the size of DT intersect QT for exact overlaps, plus a parameter alpha times the number of synonym-only hits, which are DT intersect EQT, excluding QT. Sorting by this combined score yields a balanced ranking that favors exact tokens but rewards meaning captured by synonyms. Increasing alpha prioritizes semantic matches more and will promote paraphrase documents. Decreasing alpha emphasizes literal keyword overlap and offers faster, more deterministic results. The printed top results highlight a sensible blended baseline. Tuning alpha is the single most practical lever here. A small alpha keeps behavior close to keyword matching. A larger alpha surfaces paraphrases but may pull in noisy matches. Measure results on held-out queries and tune alpha until you find the desired precision recall trade-off. Recap in 3 crisp points. Keyword search matches exact words and is fast. Semantic expansion captures meaning and improves recall. One caveat is that meaning brings ambiguity, so watch precision. Next step, tune the blend weight alpha and measure accuracy and latency on a larger corpus, or replace the synonym stage with a vector-based embedding index for richer semantics. If practical IR that scales matters to you, subscribe and watch the rest of the search series.